We're taking a look in this section at properties of numbers. A little bit of what we're going to do in this section is going to feel like, I don't know, kind of like vocabulary a little bit. There are things that you've seen before, but you might not remember the name for them because we don't often reiterate the name when we use these properties. The first one I know you've remembered. It's called like terms. So terms are considered like terms if they have the same structure, i.e. the same variable with the same exponent or exponents. So for example, on number 1, 5d and 2d are like terms because they both have the same variable d, and the d's are both raised to the exponent, understood exponent of 1. So when we have like terms, we're able to combine them. So 5d plus 2d is 7d. On number 2, while the variables are all y, some of these terms are not like the others. In particular, the first one and the last one are y squareds, but the middle one is simply y to the power 1, whether it's written or not. So it's not like the others. So we can't combine all three of these together, but we can combine the first one and the last one because they're both y squared terms. So we have 5y squared, and then we still have our plus y. Okay, so everybody remembers like terms, right? That's when we use and we use and we use and use again. It's the next set that I was thinking of when I was talking earlier. So these are considered properties of real numbers. As you look down this list, there's 7 on your list on your paper. The one that people usually remember the most is number 7, the distributive property. So you use these all the time, whether you think of them by name or not. The commutative property says the following, that a plus b is equal to b plus a. So this is a very good fact because when children first learn their addition facts, once they get high enough, right, into their nines tables or something like that, right, they go to the 9 pluses, they already know all of them because they already learned 1 plus 9 and 2 plus 9 and 3 plus 9. So they've learned most of them as they work their way up. The order doesn't matter. And it's true for multiplication as well. A times b is equal to b times a. It is worth noting that these are properties that are special to addition and multiplication. It doesn't work for subtraction, right? 5 minus 2 does not equal 2 minus 5. It doesn't work for division. 5 divided by 2 does not equal 2 divided by 5. So these are specific to multiplication and to addition. In fact, most of these are. The associative property is next. I remember that associative and commutative, associative has to do with who you're associated with. So when you talk about your friend group or whatever, you're kind of talking about grouping things together. So the associative property will always have parentheses involved. So the associative property would look something like this. If I have a plus b and then plus c, I can, without moving the order, so it's a, b, c, I'm still going to have a, b, c, I can regroup the b and the c together like this, and it will not change the value. And you might think, well, who cares? Just multiply or add the 2 first ones together and then add the last one. Well, sometimes it's easier to add a different set of numbers together. In particular, if they're numbers that add up to something nice, like 10. Right, if there's a 6 plus a 4 somewhere in there, that's easier to add up than 6 plus 7 and then add, the 4 to it or something like that. So sometimes there's a different ordering that's just quicker to work with. So this is a very nice fact. And it's true, again, for addition and for multiplication. So I can multiply a times b and then times c. Actually, let me leave the dot out. It isn't necessary. Or I can multiply the b and the c first and then multiply by the a. Additive and multiplicative identities is what really allows us to do things like getting common denominators for fractions. That's for multiplicative identity. And doing things like solving equations for both of them, actually. The additive identity simply says there exists the number 0 such that a plus 0, actually I'm going to run out of space, let me shift this down, is equal to 0 plus a is equal to a. So you can always add 0 to something and it doesn't change its value. And so 0 is called the additive identity. And then the multiplicative identity is the same kind of thing, but with multiplication. So its number is the number 1. So there exists the number 1 such that a times 1, I did it again, still not enough space, is equal to 1 times a is equal to a. And I mentioned this one is the one that we use all the time when we're getting common denominators with fractions, right? When you multiply the top by 3 and the bottom by 3, you're actually multiplying the number by 3 over 3, which is 1. You're using the multiplicative identity to do that. Kind of going hand in hand with the multiplicative and the additive identities are the multiplicative and additive inverses. So that's on my next slide. The additive inverse says that for all a, so all numbers a, there exists a negative a such that a plus negative a is equal to negative a plus a is equal to 0. And we use this when we're solving equations. Right, so if you're wanting to move something to another side of the equation, we say, well, what's the opposite of adding 5? Oh, it's subtracting 5, or it's adding a negative 5. And so we recognize that negative 5 and 5 have this special relationship that they add to 0. And it works for all numbers. The multiplicative inverse is quite similar, but instead of adding to 0, it multiplies to 1. So there is one number that does not have a multiplicative inverse. So it's for all a not equal to 0. Okay, so 0 doesn't work. There exists 1 over a. Wow. Such that a times 1 over a, or 1 over a times a, is equal to 1. And I hope as you're looking at that, you can see why 0 doesn't work. If it followed this pattern, then that we would be talking about the number 1 divided by 0, and 1 divided by 0 is an undefined value, because division by 0 is an undefined operation. The last one, the distributive property, talks about what happens when you combine, in particular, addition and multiplication or subtraction and multiplication. So I'm going to write out both of them, but I'll write them out combined. So if I have a times b plus or minus c, it doesn't matter which one, then the distributive property says, let me get a different color here, says that I can distribute the letter a, or the variable a, across, so that I multiply the a and the b, I multiply the a and the c, and the sign in the middle stays the same. And not only does the distributive property work if the multiplication occurs in front of the parentheses with the addition or subtraction, it occurs if it's behind it as well. So if I had the multiplication over here, because multiplication is commutative, it would work the same way. I can distribute it this direction. I can even write the letters in reverse order if you want, so we can write BA or AB, same sign, whatever it is in the middle, and then we've got CA or AC. The distributive property is the one that we tend to remember the name for, probably because we recognize using it as we use it, whereas the other was we're so comfortable with using them, we use them without thinking. So all we're going to be doing in this section is simplifying expressions. Now remember, we talked about this word expressions last time. Expressions means there's no equal sign. An equation has two quantities set equal to one another. These don't have any equal signs. So you're going to see a whole bunch of things where we're just combining like terms. We're multiplying, we're dividing, we're adding, we're subtracting. All we're doing is we're doing like term kinds of things. So as we take a look at, our first example, we have 4b times negative 2. And I'm going to show you what we're really doing, but I think you know what the answer is. What's the answer? Yeah, it's negative 8b. And sort of embedded in what we just did is we did two different properties. We actually did the property where we moved, you can think of it in one of two ways, where we moved the negative 2 sort of to the beginning and grouped it with the 4. That's the commutative property, where we switched the order of something. And then we regrouped so that the 4 and the negative 2 were the ones that were being multiplied in the b afterwards. So that's the associative property. So whether you're recognizing it all the time or not, the reason you're allowed to do what you're so comfortable with doing is because these properties hold. So I don't need you to show me the moving of the properties. That's not necessary. But we are using them sort of behind the scenes. Does that make sense? So looking at the second one, number 4 actually on the slide, what property do you see that we're going to use here? Yeah, that's the one we remember. We are going to distribute the 3 through, and what will we be getting?
3x minus 6.
Fabulous, 3x minus 6. Okay, everybody good with that? Okay. What about number 5? What properties do you see, properties do you see present there? There's distributive again. The numbers that we're distributing is at the end this time. So we're going to distribute the number 4 into each of the 3 terms as opposed to 2 terms. So I have 6 times 4 is 24. 4 times negative 2a, negative 8a. And then 4 times 3b, 12b, plus 12b. None of those terms are alike. That b kind of looks like a 6. I'll try it a little bit better. None of those terms are like terms because their variables don't match, right? We have a constant at the beginning, a in the middle, b at the end. So we are done. How about number 6? It's distributive again, but recognizing that this time we actually have a fraction involved, it doesn't change it, it just changes the numbers we're working with. So you might want to write down that this is 12 over 1 times 2 over 3 so that you can see it a little bit more clearly. You don't have to, but you might. As you look at 12 over 1 times 2 over 3, whether it's in this written form or before, hopefully you recognize that the 12 and the 3 reduce, right? And they both divide by 3, which leaves me with a 4 on top and a 1 on bottom. So 12 over 1 times 2 over 3 becomes what?
8.
Yeah, 8 over 1 or just 8, exactly. And then I have the 12 times the 2u becoming 24u. And again, they are not like terms because the first one is a constant, has no variables attached, and the second one does have a variable u. Okay, so what would you do on number 7? We'll distribute. So what do I get when I distribute the 3 through? 3y plus 18. Then I have a minus y on the end, right? That's still part of the question. So can I combine any like terms in this one? Yeah, I can. So the 3y and the negative y on the end can be combined. And what will that give me? 2y plus my 18. Right? Any questions on that one? Okay, so a little bit more going on as we do our last couple of examples. What did you see that we can do on number 8? Distribute the 4 through, and we can actually, in the same step, distribute the 2 through if you'd like, right? We can do both those things at the same time. So this was probably the first place where, well, maybe the last problem, to be honest, because you have the minus y after it, where you're going to have to show something because you are combining something after you do the distribution step, right? We have a distribution step here twice, and then I'm going to have to combine like terms. So if I distribute the 4 through, what does the first binomial become?
4k minus 20.
First, 4k minus, what was it, Trinity? 28. Good. And then the last one, I know somebody's already getting to the answer.
Sorry?
You're just ahead of me, Haven.
I'm sorry.
On the next one, the 2, if I distribute the 2 through, what am I going to get? 12 minus 2k. Okay, so you should have a step that looks like this. And then you should be able to look and combine like terms. So what are 2 terms that I can combine?
K's.
Yep, the 4k and the negative 2k to give me the 2k that Haven mentioned earlier. It's all right. And then we have the negative 28 and the positive 12. Those are also like terms. So what will I get if I combine those?
Minus 16.
negative 16. Yeah, it's not 24 and 12, but 28. So it is negative 16 on that one. Okay, any questions on that? All right, so the last one is actually got no multiplication involved, right, in the sense that it doesn't have distribution. But I actually have other things that make things like or unlike here. So somebody tell me two terms that you see that are like terms.
6x squared and negative 2x squared.
Fabulous. 6x squared and negative 2x squared. And if I combine them, what will I have?
4x squared.
Right, 4x squared. Fabulous. So we've sort of dealt with them. We're going to ignore them now. So tell me another two terms, or another however many terms are alike. What else do you see?
Positive 2 and negative 7.
Okay, so you can go, if you want to go in order, it's totally fine. There's a positive 2 and a negative 7. What would that give you?
Minus 5.
Right, negative 5. And then my last pieces that I haven't dealt with so far are the negative x and the negative 3x, which are
Negative 4x.
negative 4x. It's fine if you leave it like that. Some of you are like, oh no, that's not working for me. So it's a little bit more of a natural ordering to write it as 4x squared minus my 4x minus 5, because the decreasing order of exponents is a more natural way to leave the problem. I do not care. That is not the point of what we are doing right now. So either of those are perfectly reasonable answers. Any questions on like terms? Okay, let's take a look at homework number 6.